I'm going to be talking about word problem intervention. I'm going to talk about some of the research that we've done that has been sponsored by the Eunice Kennedy Shriver National Institute of Child Health and Human Development. Word problem solving reflects the capacity to apply mathematical ideas in everyday life and in science, technology, and engineering. Word problem solving may also support advanced mathematics learning as children progress through school. So, for example, in a very large national survey, US Algebra 1 teachers considered how well students were prepared and how important 15 math skills were. And teachers rated word problem solving highest in terms of supporting student success with algebra. So it's not surprising, therefore, that word problem solving is a strong age predictor of wages and employment in adulthood. But word problem solving difficulty is widespread, and that difficulty can occur even when arithmetic or calculation skill is intact. And when we have word problem difficulty, even with strong arithmetic and calculation skill, that may arise because word problem solving engages more cognitive resources than arithmetic does. A common misperception among teachers, though, is that improving teachers' calculation skill will result in better word problem solving. And because of that, in some classrooms and in many interventions, explicit word problem strategies are not taught. That's unfortunate, and that's illustrated in a large randomized controlled trial that we conducted in 2013 with at-risk first graders. Here, with intervention, the effect of arithmetic intervention on word problem solving was modest, even though the effect on arithmetic was substantial. So the main focus of the intervention was number knowledge and arithmetic strategies. And we expected an improved outcome on arithmetic, but we were also interested in how well that improved number knowledge and arithmetic skill would translate into improved word problem solving. So we were very interested in the fact that the effects on word problem solving were much smaller. And while the intervention narrowed the post-intervention arithmetic achievement gap, the word problem gap widened dramatically. So by the end of the school year, students who were at risk at the start of the study had become much closer in range to their classroom peers on arithmetic, but at the end of the year, they were much farther behind on word problem solving. So this suggests that although arithmetic is foundational to word problem competence, arithmetic is not a sufficient pathway for at-risk students. And that makes sense because word problems require text processing to build word problem models and to generate the number of sentences before calculations can be applied. Because language comprehension is necessary for text comprehension, it makes sense that language comprehension plays a stronger role in word problem solving than in arithmetic. And this has in fact been shown when studies assess in the same study, they look at the relation between language comprehension versus calculations versus with problem solving. So for this and for related reasons, word problem solving is sometimes conceptualized and studied as a form of text comprehension. So what I'm going to do in this talk is explain a randomized controlled trial in which we tested the effects of a word problem intervention that treats word problem solving as a form of text processing. And we did that by incorporating into the word problem intervention an explicit focus on language comprehension. In explaining this randomized control trial, I'm going to describe the core features of our approach to word problem solving intervention, which relies on schema instruction. And at the end of the talk, after I finish talking about describing the randomized control trial, I'll provide you with additional information on our word problem interventions and the grade levels and types of word problems that our word problem interventions address. So the title of the study I'm going to tell you about is Embedding Language Comprehension Instruction Within Word Problem Intervention. And it was published in 2020 in the Journal of Educational Psychology. You can see who the various authors on this paper are, and you can see the grant that supported this work, and it's from the National Institute of Child Health and Human Development in the National Institutes of Research. So the first thing I want to talk about, and I think somebody, one of the teachers who's participating today, or one of the districts actually asked, should we be focusing on word problem intervention at first grade? And we think the answer to that is yes. First grade number knowledge intervention with speeded arithmetic practice dramatically narrows the arithmetic achievement gap. But as I mentioned, at the same time, across first grade, if we don't explicitly teach word problem skill to at-risk learners, the word problem achievement gap will widen dramatically. And this is problematic because word problems represent a major emphasis in almost every strand of the math curriculum. And as I said before, word problem performance is a strong predictor of wages in adulthood. Even so, early math research has focused dominantly on number knowledge and arithmetic with only minor focus on word problems. And when those interventions focus on word problems, it's usually in the service of supporting number knowledge rather than teaching at-risk learners specific strategies for thinking about and solving word problems. So the second question is, well, if we're teaching word problems, why focus on language comprehension? Well, word problem solving is viewed as an interaction between language comprehension processes and math problem solving strategies. And when researchers have modeled faulty problem solving with math problem solving errors versus language comprehension errors, it turns out that correct problem solving depends more on language comprehension than on math problem solving. And changing wording in a word problem in only minor ways dramatically affects the accuracy with which students solve those problems. Now, a common assumption in schools is that students have the language comprehension they need for understanding word problem statements and for building an appropriate word problem model. But for at-risk learners, this assumption is shaky. And this suggests that an instructional focus on language comprehension processes, as well as the mathematical aspects of word problem solving, is needed. Well, the next question is, why might we embed language instruction then in word problem intervention instead of providing conventional language therapy for these children? Well, language therapy improves oral language comprehension, but research in reading and math has shown that transfer to academic performance is limited. And that's despite a strong association between language comprehension and academic performance. So why might transfer from language therapy to academic performance be especially difficult for at-risk children? Well, first of all, they have an inadequate foundation of academic skill. So expecting them to learn about language and become, due to that language therapy, better at word problem solving is not realistic when they simultaneously do not have a foundation of math understanding and math skill. And second, at-risk learners, a signature feature is that they have substantial challenges with transferring the knowledge they learn more generally. And that argues for embedding language instruction in the context of direct skills, here word problem solving intervention. So in our study, and I'm going to tell you a little bit now about the math component of in this study in which we taught word problem solving. So in this study and in our work on word problems generally, we rely on schema instruction. Schema instruction explicitly teaches step-by-step problem-solving strategies that reduce demands on reasoning and working memory. And this includes strategies to help students understand word problems as belonging to word problem types. And it also includes strategies for building word problem models. And I'll tell you a little bit about this. At first grade, we address the three major word problem types that are found in the curriculum at first grade. So the first problem type is a total problem where two or more parts are combined to form a total. The second word problem type we refer to as difference. It can also be called the compare problem, where two quantities are compared to find a difference between them. And a change word problem type, where an event occurs to increase or decrease a starting amount. So for each of these problem types, we teach the mathematical structure, and we do that by we begin by role-playing the problem type's central mathematical event. We do that using intact number stories that do not have any missing quantities. And in those intact number stories, we use concrete objects to illustrate the mathematical event, and we do that using the child's and the tutor's names. We connect to and build on those role-playing experiences by connecting the central mathematical event in that problem type to a visual schematic into which story quantities can be entered. But we fade that quickly and use the visual schematic only as needed. We replace the visual schematic with a hand gesture that quickly reminds students of the schematic and of the mathematical the central mathematical event. So two parts joined together to form a total, a compare problem where there's a difference between two quantities, and a change problem, we have a starting amount that increases or decreases to give us a new ending amount. And we also connect the central mathematical event to a problem type sentence. So for a total problem, we have part 1 plus part 2 equals total, or P1 plus P2 equals the total. We have the difference problem type sentence. The bigger number minus the smaller number equals the difference. And we have the change problem type sentence. The starting amount plus or minus the change equals the end amount. And after students have had experiences role-playing and using the role-playing scenarios in connection with these mathematical representations, visual, schematic, hand gesture, and the problem type number sentence, we then introduce problems which have missing quantities using role-playing, the problem type schematic, the hand gesture, and the problem type sentence. And we then teach step-by-step strategies to structure the process by which students, when faced with a word problem, build the word problem model and solve for the answer. They're taught to, we teach students to run through the problem, read the problem. Not all students read the problem, so we teach them to read the problem or to listen to the problem. To underline the word that indicates what the problem is mostly about, and to name the problem type. Once they've deciphered, processed the text, thought about what it's about, named the problem type, they write that problem type's sentence. They enter relevant quantities from the word problem statement into the problem type sentence, while they cross out any extra or irrelevant numbers, and they solve for the missing quantity. So here's what it looks like. This is a total problem where two parts are being brought together to form a total. Kathy has 5 pencils and 3 erasers. Pamela has 7 pencils. How many pencils do the girls have in all? The child writes T, so underlines pencils, that's what the problem is mostly about. Writes a T to help her remember that this is a total problem where two parts are being put together. Writes the problem type sentence, part 1 plus part 2 equals T. Fills in relevant numbers while crosses out the extra irrelevant number. You see where that's crossed out with 3. And then finds the missing number, solves for that missing number, which is 12, and then writes a label for that numerical answer, pencils. Here you see a first grader's work. It's also a total problem. 4 girls and 3 boys are playing on the swings. They swing for 10 minutes. How many children are playing on the swings in all? You see that the child underlined children because that's mostly what this problem is about. The child crossed out 10 because that's an irrelevant number. She wrote the number sentence P1, the problem type sentence, P1 plus P2 equals T, and then filled in the relevant parts, wrote X to signify the missing number, and then solved for that missing number, which was 7. So that gives you some idea of the mathematical schema-based instruction with which we teach very young children, first graders, systematic structured strategies for solving word problems. And into that instruction, we are embedding vocabulary and language instruction to help children understand the kinds of vocabulary and language construction challenges they'll face as a function of problem type. So for combined or total problems, we teach the students explicitly about joining words like all together and in all, and what those joining words mean and how they connect to a central mathematical event that occurs in total problems. We teach children about superordinate categories, such as dogs and cats equal animals, or boys and girls put together equal children. That's helpful vocabulary that is rarely explicitly taught in the context of total or combined problems. We then will work on compare problems. As we're teaching compare problems, we're teaching compare vocabulary and language constructions. So we'll help children understand words like more, fewer, than, ER words. We teach children about adjective ER words versus noun ER words, like bigger versus teacher. You can't just look for those ER words. You have to understand the gist of what's happening in the story. For change problems, we teach cause and effect conjunctions like then and because and so, and how that connects to a cause and effect mathematical event that changes the numerical value by increasing or decreasing that value. We also teach children about implicit quantity change verbs, like when things cost something, that means that your money value is decreasing. Or if you ate something, the available food has decreased. Or if you found something, the quantity that you have will increase. And we teach time passage phrases and help children be sensitized to that, how that connects to cause and effect. 3 hours later, the next day. And then we also teach confusing cross-problem constructions. We sensitize students to the idea that than and then do not mean the same thing. And this is a big stumbling block in the at-risk learners we work with. So we teach explicitly the difference between what those words mean and how used in context, more than means something very different than more. And then we also talk about tricky labels. So questions where there are superordinate category words, questions where the label is not even provided, or a noun in the question that's actually going to turn out to be a nonsensical label. So before I move off of the embedded language instruction, I think it's important to emphasize that we, in this intervention, the embedded language instruction, we are not teaching vocabulary and language construction as keywords. A lot of teachers teach word problems by teaching children that words like more mean add, and a variety of keywords, and children will often look for those words, pull out numbers, and either add or subtract or multiply or divide, depending on the keyword, the operation that is associated with that keyword. We don't do that. Instead, we explicitly teach children why searching for keywords and numbers without reading the problem or figuring out the problem type often produces the wrong answer. And we illustrate this and help children appreciate the problem of thinking about keywords for solving word problems by having them check the work of other children. So these are actually worked problems we've prepared. And students find errors and they explain how and why the errors occurred. And the kinds of errors in these worked examples that the students are looking for is reliance on keywords that caused the problem solver to select the wrong operation, the misuse of irrelevant numbers, and failing to recognize that a problem actually has two steps, so two different operations in the same problem. And I'm going to spend a little bit more time on why embedded language comprehension instruction is not keyword instruction by showing you a series of total problems and helping you appreciate that if you're looking for a keyword, it's going to trip you up. So here's the total problem. Frida has 8 roses. Each rose is 12 inches long. Henry has 5 daffodils. Each daffodil is 4 inches long. How many flowers do the children have altogether? Well, some children might be tempted to use altogether as a keyword and to pull out numbers that go along with the flowers in the word problem. And if they did that in this problem, they would be successful. So part 1 plus part 2 equals total. There are 8 roses and 5 daffodils, so 8 plus 5 equals 13 flowers. But this next problem is also a total problem. Frida and Henry have 13 flowers altogether. Frida has 5 roses. How many flowers does Henry have? Well, if you're using altogether for adding, to signal adding, and you take the 5 and the 13, your answer will be wrong. It'll be 18, because here in this total problem, the child has to subtract to find a difference. So the problem type sentence is the same. Part 1 plus part 2 equals total, P1 plus P2 equals T. But here, when you fill in the missing numbers, the provided numbers, and identify the missing number into the P1 plus 2 equals T number sentence, X is missing, plus 5 equals 13. In this problem, we know the total, but one of the parts is missing. So altogether does not identify the correct operation in this problem. And if you look at the third bullet, this is also a total problem. Frida has 8 roses. Each rose is 12 inches long. Henry has 5 daffodils. Each daffodil is 4 inches long. How many flowers do the children have? Well, problem type vocabulary is not found in this total problem anywhere. So relying on keywords is not going to help you in this problem. And then the final example is a total problem. Frida has 8 roses. Each rose is 12 inches long. Henry has 5 daffodils. Each daffodil is 4 inches long. Lola has 4 tulips. How many flowers do the children have altogether? Well, here you have to figure out, if you grab numbers thinking that you have P1 plus P2 equals T, you will realize that there is actually a third part in this problem. So a superficial strategy of looking for 2 numbers doesn't always mean that this will not always work for you. In this situation, there's 3 numbers and 1 is relevant. All 3 are relevant. So now I'm going to tell you a little bit about the study. In this study, at the beginning of 1st grade, we identified children with low arithmetic and low math concepts applications. That's how we define risk. There were 400 children who entered the study and were randomly assigned to 4 conditions. So word problem intervention was one condition, word problem intervention with embedded language instruction was a second condition. We had a third condition, which was number knowledge intervention. And we wanted that to answer the question, is transfer from number knowledge and arithmetic to word problems sufficient to support word problem outcomes? And we had a control group, which was the natural school program. And many of the children in this study were receiving math intervention as part of their school program. And each of the 3 active conditions, so the first 3 bullets, those conditions lasted 15 weeks, 3 sessions per week, 30 minutes per session. And each of those 3 conditions included a small component of speeded strategic arithmetic practice because we wanted all 3 conditions to be competent, the students to be competent in arithmetic skill, which is necessary, although not sufficient, for strong math word problem solving